We have studied in depth the area under a curve bounded by the x-axis. In today's lesson, we will extend this concept to the area between two curves. We will also learn how integrating geometry into this type of exercise can make finding the solution a lot easier. Hi, my name is Tom Atwater. Let's start today's lesson by examining an illustration. We have two curves, y equals f of x on the top and y equals g of x on the bottom. And what we're going to do is look at finding the area of the curve, or of the region, which I'll label R, which starts at the x value of A and goes to the x value of B. So that shows our boundaries, and of course the upper boundary is the curve for y equals f of x, and the lower boundary is the curve y equals g of x. So that region R, bounded by the red lines, is what we want to find the area for. So now let's take a look at what we want to do in order to set up the calculus of finding that area. We want to divide it up into rectangles, something we've been doing earlier. And this time the rectangles are going from the lower bound up to the upper bound. And again, we're going to divide the rectangles up and then look at calculating the area of just one of these rectangles. So the way we look at this is we are going to take a particular c sub k, right here is my x value, c sub k. And we need to evaluate the upper function, f of c sub k, and we need to evaluate the lower function. And what that's going to give us is essentially what I would call the length of our rectangle. Our width of the rectangle, of course, is the delta x. And you can see down here, I'm showing you that we multiply length times width for the area of the rectangle, and then what we're going to do is look at, as delta x goes to 0, the limit of what would be the Riemann sums as delta x goes to 0. And of course we know that's going to turn into an integral. So here we have it, definition of the area between curves. If f and g are continuous with f of x greater than g of x throughout the closed interval ab, then the area between the curves y equals f of x and y equals g of x from a to b is the integral of f minus g from a to b, and that's what we have down below, that the area is the integral of f of x minus g of x dx evaluated from a to b. All right, that's great. Let's start off with an example then where we use this formula for finding the area between two curves. Find the area of the region between the two curves from x equals 0 to x equals pi over 4. And we have y equals secant squared x and y equals sine x. Let's look at the graph for this, because that helps us to set up and see what it is we're actually doing. So our upper curve, you can see, is y equals secant squared x, and the lower curve is y equals sine x. So we're going to set up an integral, which is going to be the integral from 0 to pi over 4. And that we can see here and here are two limits of integration. And we're going to take the upper curve, so secant squared x, and we're going to subtract the lower curve, minus sine x, and integrate that with respect to x. So now we have to do the anti-differentiation. So the integral of secant squared x is tan x, and the integral of negative sine x is plus cosine x, and we're evaluating from 0 to pi over 4. And when we work that out, we will end up with an area of the square root of 2 over 2. All right, Well, that was great. We now see how we can find the area of what we could consider an irregularly shaped curve by using the integral. Let's take a look at another example, and we're going to find the area of the shaded region analytically. And so we have this two graphs, again, our two curves, y equals 2x squared and y equals x to the fourth minus 2x squared. And what I want you to notice is this is a symmetrical graph, which means that what I can do is integrate it from 0 to 2, which would give me this area that I will shade in slightly. And because it's symmetrical, all I need to do then is double that area. So again, we've set up our integral from 0 to 2. And I'm going to double it. And that's going to be 2x squared, the upper curve, minus 4x, I'm sorry, not minus 4x, minus x to the fourth. Let me fix that. X to the fourth minus 2x squared. And that's all, again, with respect to x. Okay, so let's continue simplifying that. We would have twice the integral from 0 to 2, and I'm going to have, notice that I have a 2x squared plus another 2x squared here. So that's going to give me and because it's a double minus, it's going to give me 4x squared. So I have 4x squared minus x to the fourth dx. And so my integral then would be, or my integration would be 4x cubed over 3 minus x to the fifth over 5. And that's going to be evaluated from 0 to 2. And, of course, then we have to double that. When I work that out, it gives us an area of 128 divided by 15. All right, that was great. Now, when a region is enclosed by intersecting curves, the intersection points give the limits of integration. And we could see that we were given them here. We're going to do an example where we're going to have to find those points of intersection. And we'll talk about that shortly. So let's go on to the next example. Use a calculator to find the area of the enclosed region. And we have y equals sine x and y equals 1 minus x squared. Of course, the sine curve we're very familiar with, as well as the parabola that opens in the downward direction. So we're going to use the calculator because we need the calculator to find the x value at this point of intersection. And we need the calculator to find this x value for this point of intersection. And of course, you should now see that what we're finding is the area of this region right here. All righty, so let me switch to another screen here, and let's actually see what the calculator gives us as answers. We plug in those two, we ask it to find the points of intersection, and it'll come up with and tell us that this x value is equal to negative 1.09624. And what I did on my calculator is then I stored that into, and I just arbitrarily picked the A spot to store that. And then for this point right here, the calculator gives us 0.63673,265, and this time I stored it into B. And so now I then use the calculator to do an int problem where, in terms of the graph, we're going to subtract, we're going to take 1 minus x squared and subtract sine x. So that's the function that I entered into the calculator. And the variable, of course, is x, and we're integrating from a to b. So it just made, by storing those values in a and b, it made it easier for me to plug my numbers into the calculator because I could just use a and b as those limits of integration. Once you plug all that in, excuse me, and you press enter, then we get an answer which is 1.67 for the area of that region inside right here. Okay. All right, that was great. Now, if a boundary of the region is defined by more than one function, we can partition the region into subregions that correspond to the function changes, and then proceed as usual. So let's take a look at an example where we can do this. Find the area of the region R in the first quadrant that is bounded above by y equals the square root of x and below by the x-axis and the line y equals x minus 2. So the picture of this is here. We can see that we have two distinct areas that I want to deal with. And the reason that we need to deal with two distinct areas is as we start at 0 and get to the point of 2, you can see that the bottom boundary, and let me use this red pen, the bottom boundary here all of a sudden changes, and it becomes this line right here. And so we have two separate areas that we're going to integrate here. We're going to go and take the integral from 0 to 2 of this upper curve, which is the square root of x, minus, well, what are we going to minus? We're going to minus this, which of course is just 0. So we can leave that section as it is. So dx. Plus, now we need to integrate from 2 to 4 the area which is bounded by the upper curve, square root of x, minus the lower curve, which is y equals x minus 2. And again, that's with respect to x. And so that's our integrals, or the two integrals that we will sum together in order to find the total area. We'll add those. Okay, so I've cleaned the area down here so that I can finish off finding those integrals. So remember that the first integral we had was the area given by the integral from 0 to 2 of the square root of x. So what that gives us is 2/3 x to the 3/2 and evaluated from 0 to 2. And to that we had to add the second area right here, which will give us, again, the square root of x yields the same integral as we just did. Then we have minus x squared over 2 for this x. And then for the plus 2, we'd have plus 2x. And that's being evaluated from 2 to 4. And when we do all the arithmetic, plugging in the various limits of integration, adding it all together, we get an answer of 10/3. And so that would be the area of the entire region A plus B. Now, here's the same problem, except that we want to integrate with respect to y. And when we integrate with respect to y, it can make the problem a lot easier to do. So let's take a look at this picture, but set it up with respect to y. So you'll see that what happens is we have our two curves. We still have x equals y plus 2, which has been rearranged from the original y equaled x minus 2, and we have the curve x equals y squared, which came from y equals the square root of x. And so what happens now is we set up our rectangle where the length here is figured out as f of y, y, and subtracting g of y comma y. And so what we have is f of y minus g of y for our length. Now the width is, instead of delta x, it's delta y. We still do the integrals in the same fashion, which is we're going to multiply the length times the width, and that would be f of y minus g of y times delta y, and then we integrate with respect to y. And the other thing to realize then is our limits of integration start at 0, and for this problem, they go up to 2. So let's actually set that up and look at what that integral would look like. We would have the integral from 0 to 2 of y plus 2 minus y squared, and it would be dy. So then we integrate this with respect to y, and we end up with y squared over 2 plus 2y minus y cubed over 3, and that's being evaluated from 0 to 2. And when we do that whole set of arithmetic, yes, of course, we get the answer 10/3. And what I'm hoping that you see by doing it with respect to y is, first of all, we only had one integral to deal with. In addition, that integral was actually easier than it was easier than the second integral that we were dealing with when we did it with respect to x. So not only do we only have one integral, but it's an easier integral to deal with. So looking at it as a rectangle going horizontally, that is integrating with respect to y, can sometimes make the problem easier. Well, I want to take the same problem and examine it and show you how using geometry formulas can also save some time. So we're going to look at the same problem again, but this time I'm going to have us find that area of the region, but do it by subtracting the area of the triangular region from the area under the square root curve. So a little bit different instruction. Let's take a look at this picture and see how that is going to be set up. So what we have is the area of the square root of x starting at 0 and going all the way to 4. So really it includes this entire region. And then what happens is we look at the area of the triangle right here, and we subtract it off, which of course then leaves us the region that is in blue, which is the region that we're interested in actually finding the area of. So our limits of integration will be from 0 to 4. That is 0 to 4. We're going to take the square root of x with respect to x, and then we'll subtract off the area of the triangle. So let's set up this integral right now. We have the integral from 0 to 4 of the square root of x dx, because we're finding the area between the square root of x and the x-axis. So that's this. And then we have to subtract off the area of the triangle. And the area for triangle is 1/2 base times height. So it's 1/2 2 times 2. 2 was the base, and 2 works out to be the height. So what we have then is 2/3 x to the 3/2 evaluated from 0 to 4 minus 1/2 of 2, of course, is 1, so 1 times 2 is 2. And yes, of course, when we work this out, you will get the same answer of 10/3 for the area of that region. All right. Well, you should clearly see that from the 3 different ways that we solved that same problem, that you have options for finding the area of a region, some of which may be easier than the others. Well, now it's time for you to try a problem. I would like you to find the area of the region by subtracting the area of the triangular region from the area under the larger region, and then the region on or above the x-axis bounded by the curves y squared equals x plus 3 and y equals 2x. Draw a diagram or have your graphing calculator help you with that to see how to set it up. So pause the video while you work on this problem, and when you are finished, restart the video to check your solution. All right, let's find out how you did on this problem. I plugged the 2 equations into my graphing calculator, and I came up with this, or it came up with this diagram. And so let's take a look at this in detail. We can now see that we have a point of intersection here, which is equal to 3, and that's with the x-axis and my curve for y squared equals x plus 3. Then for my other curve of y equals 2x, right here, is where it intersects, and that is the point 1, 2. And maybe I should do the same here. That's 3, 0. So what we're looking for is this region inside of here. And what I originally told you in terms of setting up the problem is that I wanted you to find the area of the entire section between the curve y squared equals x plus 3 and the x-axis, and then subtract the triangle. Now, some of you may have noticed that you could also do this by integrating with respect to y. And that would be similar to the example that I showed you earlier. So again, you have options here. You have the method of subtracting the triangle. You have the method of doing it with respect to y. Both of them give us the same answer. Let's actually look at what happens if I do it with respect to y. What I would have then is the integral from 0 to 2, and my curves. Remember, my curves that I started with were y squared equals x plus 3. That would give me x equals y squared minus 3. And my other curve was y equals 2x. So that would give me x equals y over 2. So I would need to take y over 2 and then subtract y squared minus 3. And I would integrate it with respect to y. So what I now have is y squared over 4 minus y cubed over 3 plus 3y. And I need to evaluate that from 0 to 2. When I work all of that out, I will get an answer of 13/3, which is the answer that I hope you got when you worked it out by taking the area of underneath the whole curve and then subtracting off the triangular area. Either way, it's your choice, whichever way you seem as the easier way to do it. Well, that was a great job today. In this section, we talked about the area bounded by two curves. And we looked at using geometry as a method for helping us to find certain areas, but also looked at integrating with respect to y instead as a possible way to make it easier. Be sure to work the exercises that your teacher assigns, and we'll see you next time.